Yes, sir.
Yeah. So let us begin. So lecture 11 today. Okay. So we've been looking at jets and jet-related phenomena like superluminal motion, Doppler boosting, and so on. So jets naturally transport particles and energy, relativistic particles, and therefore energy are pumped out of the AGN at very, very, very high velocities. Because of the high Lorentz factors, the energies of these particles is very high, and they are able to create shocks, and these shocks are able to propagate through the interstellar medium and create an impact in the form of feedback. So in this slide, what we are trying to summarize is the impact of AGN feedback from these jets on the evolution of the entire galaxy as a whole. Right? So suppose you start with a normal galaxy, right? It has a supermassive black hole at the center, but it's a dead quasar, which means the supermassive black hole is inactive at the present time. According to the hierarchical model of galaxy formation, galaxies grow in size through hierarchical growth through galaxy mergers. These galaxy mergers can be major mergers, which are mergers of galaxies of comparable mass, or minor mergers, which are mergers between a more massive galaxy and a much less massive galaxy. These kind of mergers we know were much more common in the past than they are now. And when these galaxy mergers happen, that leads to gas inflows, because typically there will be some gas in each of the two galaxies that are merging. And due to the gravitational potential and the perturbations caused by the merger itself, there can be gas inflows triggered into the center of the galaxy. Once gas is pumped into the central region of the galaxy, because of that gas inflow, two things can happen. One is starbursts can be triggered, which means extensive star formation happens in the central region of the galaxy, fueled by the influx of gas. And at the same time, accretion onto the quasar will start. The gas accretion, once it starts, that leads to growth now of the black hole itself, right? that will also lead naturally to mergers of the two black holes. So that's another method by which the black hole will grow, both by accretion and by mergers triggered by this merger of galaxies and the following gas inflows. What will happen to the sleeping quasar? So the sleeping quasar, of course, will become activated. It will go live. It will likely produce jets. And those jets will start producing AGN feedback, which means they will start pumping energy back into the surrounding medium. When that happens, that will stop further inflow of gas. And that can also, in cases, be strong enough to push back the gas that has infallen. So even though it is at the bottom of the potential well, some of the gas can get thrown out. And what will that impact? How will it impact star formation? It will naturally reduce the star formation because gas, which is the fuel of star formation, that is no longer available in the quantities that it was previously. So star formation rate will go down in the galaxy. And what will happen to the quasar itself? Because the accretion, the gas in the regions surrounding the supermassive black hole is now lesser in quantity, the accretion rate will go down and the quasar will begin to fade. And if the feedback is really strong, what will happen? Most of the gas around the quasar will be expelled to distances far away from the quasar, and you will go back to your initial condition, your starting point, which is a normal quiescent galaxy with a dead supermassive black hole sitting at the center. This whole cycle need not happen only once in the lifetime of a galaxy. It can happen multiple times. So there can be multiple mergers, multiple episodes, therefore, of star formation and the triggering of the activity in the quasar. By quasar, I mean generically the AGN. Then the AGN may produce feedback, and then that may throw away gas, quench the star formation, reduce the activity of the quasar to nearly zero, and then you go back to the starting point. So this kind of scenario looks very convincing and attractive. However, it has to be tested. And how do we test it? See, remember, there are a lot of processes here, star formation, etc., as we saw, because of coupled differential equations, which are very difficult to solve analytically. Everything is done numerically these days. And therefore, you take recourse to numerical simulation, which will show you what exactly happens. And there are people working on these kind of simulations. So this image comes, this particular diagram comes from Philip Hopkins. So Phil Hopkins is one of the leading researchers in this field. And there are people who work on specific aspects, people who only work on how the quasar is triggered. There are people who only work on astrophysical jets and figure out through numerical simulations how energy and matter is expelled from the central regions of the galaxy. There's only people who look at star formation triggered by the infall of gas. The only people who look at mechanisms by which this gas infall may happen. So you may have gas infall preferentially happening through a galactic bar or some other structure. So there are people who model only the galaxy merger itself on very large macroscopic scales, taking into account everything, the metallicity and so on. There are people who only look at the chemical evolution of the problem. So because of this, what happens in every cycle that you go through this circle, every time more and more star formation has happened. And whenever star formation happens, that enhances the metal content of the gas. So the gas phase metallicity, as it is called, increases. And when the gas phase metallicity increases, that leads to presence of metal lines in the emission lines of the quasar, as well as in star formation. So you can actually trace the gas phase metallicity directly through observations. So there are people who only worry about whether the metallicity, or as it is called, the chemical evolution of the galaxy is happening correctly or not. So although the big picture has now been confirmed, the structure or the evolution map that is sketched in this figure is now broadly believed to be correct, as evidenced by numerical simulations and supported by corresponding observations. So we shall see a few examples of what kind of observations you can do to test the hypothesis that you have for the structure of the active galactic nucleus. Okay. So far we've talked about jets, we've talked about the properties of the supermassive black hole, and we've talked about the accretion disk that surrounds the supermassive black hole. Now we've also hinted at that there must be something on the outside of the accretion disk. Okay, what happens when the accretion disk ends? So if AGN consisted only of this, right, we would see just X-rays and UV radiation from the hot accretion disk. We would see the jets and nothing else. But what has been known for a long time now is that there is strong infrared emission from the AGNs. And we know that the accretion disk, even on its outer perimeter, is not cold enough. We know the temperature profile of the accretion disk. We know that even at its outer end, the accretion disk is not cold enough to emit significant amounts of infrared emission. And therefore, addition to this model was proposed, which is that their model must include a torus of gas and dust that surrounds the central engine. Why gas and dust? Why isn't there dust in the accretion disk? It's simple to understand, because the accretion disk is too hot. And above a certain temperature, the dust gets completely decimated, okay, and cannot exist. We shall see what that temperature is in a minute. So these dust particles, which we assume to be composed of grains of graphite, get heated by the radiation from the central engine until they are warm enough to radiate energy at the same rate at which they receive it. Dust gets vaporized or sublimates at temperatures of about 2000 Kelvin. And this will have a peak emission at about 1.5 microns, which will be, thermal emission will be in the near infrared bands. So anything that you see, any emission that you see at wavelengths longer than 1.5 micron must be predominantly coming from dust, which is at a temperature cooler than 2000 Kelvin. Okay. We have always approximated emission from the sun or from other stars as a black body with a temperature corresponding to the photosphere of the star. Can you treat dust as a black body? Yeah, you have to obviously justify. If you say yes, why yes? If no, why no? Do you think it's, let's take a specific example. You have this accretion disk. On the outer side, you have a torus, okay, and which is at a fairly high temperature for dust, but below 2000 Kelvin, because that's the sublimation temperature of the dust, right? Now, just tell me, for this torus, if I just take the emission from the torus, and imagine for a moment I can somehow subtract the emission from jets, accretion disk, etc. And I'm only looking at a hot torus, which is shining in the infrared. Can I approximate that emission as a black body? What do you think? I mean, it's either yes or no. Okay, let me rephrase the question. Do you think the dust will all be at the same temperature?
No, sir.
Huh? No or yes?
No, no, sir.
No. So there will be, just like you had a temperature profile for radial temperature profile for the accretion disk, you will have a temperature profile for the dust. So the dust which is closer to the black hole will be hotter. The dust which is farther away will be cooler, right? So, but if you take dust in annuli, in rings, will that be a black body? Yes, because it will all be at the same temperature, and just like in the accretion disk, each individual thing will be at the will be a thermal black body. But as the temperature gradient changes, you will have to approximate it as the sum of black bodies at different temperatures. So unlike the range of temperatures that you find in the accretion disk, okay, which goes from 10 raised to 5 Kelvin at the center, okay, to about a few thousand Kelvin at the edge. The range, the dynamic range is quite small in the dust. And because of that, it is not too wrong to take it as a black body, but very often it is approximated as what is called as a gray body, which means it's the sum of black bodies, many black bodies at slightly different temperatures. And that is what is done for the dust. We can define what is called as the sublimation radius of the dust, which basically tells you how far away from the black hole the dust can survive. Right? So if the dust has a luminosity L, then at a flux, then the flux at a radius R will be just L over 4 pi R square. Now this, if there is a dust grain sitting at a of radius A, if it is sitting there, it has a cross-sectional area. Suppose it's a spherical dust grain of radius A, it has a cross-sectional area of pi A square, because that is therefore the area that will capture the radiation that is coming from the central engine. And the power absorbed will be simply pi A square times L over 4 pi R square will give you a LA square over the pi's cancel out over 4R square. Now what will happen when this happens? The temperature of the dust grain will rise until the power of the thermal emission emitted by the dust grain is exactly equal to the power that it is absorbing. If the dust grain behaves like a black body, and there is no reason to believe that an individual dust grain behaves as a black body, provided you assume that it's at a single temperature over the whole grain, which is a very reasonable assumption, because remember the dust grains are very small, so they reach temperature equilibrium very, very quickly. If you do that, then you can equate the energy absorbed to the energy emitted, which is just given by the Stefan-Boltzmann law, and multiplied by the surface area of the spherical grain, 4 pi A square this time. So if you do that, you can write an expression for R, which is the sublimation radius, and that depends on only two things. It depends on the luminosity of the central engine, and it depends on the temperature of the dust. So warmer the temperature, sublimation temperature of the dust, closer will be the radius, and the lower the sublimation temperature, the further away will be the radius. So what is the sublimation temperature? It's the temperature at which, above which, the dust grain gets destroyed. So so one can work out, there is a problem in your assignment which asks you to calculate this for a typical AGN.
Hello, sir.
Yeah.
Sir, why the sublimation radius doesn't depend on the materialistic properties of the dust?
if it's a black body, it won't depend on the materialistic properties of the dust. Why would it? I mean, if you have a silicate dust particle, or if you have a graphite particle, dust particle, it won't depend on that, because we are assuming the particles are small enough that they reach temperature equilibrium almost instantly. So we don't have to worry about the conduction in the grain and so on, in the individual grain. So they're both black bodies. Once you assume that they're both black bodies, whether they're made up of graphite or silicate, it will not matter too much, right?
Sir?
Yeah.
So the T here is the sublimation temperature, right?
T is the sublimation temperature, correct. Yeah, maybe I should have put a, do that in modify the slide. Okay. So now this is the sort of revised picture that we have for what's happening. There is a central black hole surrounded by an accretion disk at different temperatures. Closest to the black hole, the temperatures are very high, 10⁵ Kelvin. So they are emitting in far UV and soft X-rays and so on. As you go outwards, the UV, it is predominantly in the UV and eventually in the optical. And this, because the luminosity goes as the fourth power of the temperature, there is a lot of emission which comes in the far UV, and that leads to the presence of the UV excess, which we have seen in all kinds of AGN. They sort of, once you go to the UV bands, rest frame UV bands, they become very bright because we are seeing the emission from this accretion disk. The mid-infrared and near-infrared and even part of the far infrared emission from AGN is explained in terms of obscuring dusty torus. This torus idea, I think, it's a bit overdone in the sense that it may not be a torus that the shape is correct on the inner side, but on the outer side, it may be a torus that extends for very large distances and slowly disappears. It may not be, there is no reason to expect that the outer edge will be a perfect shape, a rounded shape like it is shown here. But definitely there is an obscuring dusty torus. And we need a torus rather than just an obscuring dusty sphere, because we need a mechanism by which the jets can escape easily. We also expect the torus to settle in the same plane as the accretion disk because of just angular momentum type arguments. Remember, unlike the accretion disk, which is geometrically very thin, although optically thick, the torus is optically thick and geometrically thick. It's a fairly thick object. Now, what is the scale of the thing? So in one of the early lectures, I said that the supermassive black hole, even the most supermassive black hole that you can imagine, does not have a Schwarzschild radius larger than the solar system. Okay, solar system taken really a big solar system. I mean, a loose definition of the solar system. Let us say something with a diameter of about 200 AU, pretty large. That's the size of the Schwarzschild radius of the largest known black hole. The accretion disk starts out from there, right? So 200 AU corresponds to approximately 1 milliparsec, right? The accretion disk starts out from there, from 1 milliparsec or 0.001 parsec, and goes a few times that because of the inner most stable radius arguments. So let's say 0.003 parsecs and goes out to about 0.2 parsec. So that's the size of the accretion disk. Beyond 0.2 parsec is the regime of the dusty torus. And even the dusty torus itself doesn't extend to beyond a few parsec. We don't know exactly what its outermost limits are, but it's obviously not large enough to be resolved with any telescope that we have, at least any infrared telescope that we have at the moment. But if you look at some of the elliptical galaxies, so this is a elliptical galaxy called NGC 4261, which also happens to be a radio galaxy. There, if one looked at the core of this galaxy with the Hubble Space Telescope, you see a dust disk. Okay, this disk, I should caution you, is not the torus. What we are seeing is not the torus. It is a dust disk that surrounds the torus. The true torus itself is unresolved and somewhere here, because as we said, the size of the torus may be a few parsec. This thing is 250 parsec in diameter. So it's about 100 times larger than what you would expect the torus to have. So as I said already, we don't have a telescope that will resolve the torus for us at the present time. Except in one case, which we will come to later. The radio structure of NGC 4261, this is also good because our expectation, as we said, is that so both A and B panels, they have the same orientation, of course not the same scale. Number B is a highly zoomed in version of the center. But what we can see here, that the radio jets seem to be aligned perpendicular to the disk. So along the rotation axis of the disk, which is exactly what we expect to see in our picture, that the jets that emanate should go perpendicular to the accretion disk and to the dusty torus. So far so good. There are a number of other galaxies where the torus can be imaged at this level of resolution. And we can see the same thing, that the radio structure is perpendicular to the torus. So now we are in a position to show this diagram, which is one of the representations of AGN unification. So we've seen very, very large phenomenology in AGNs. We have seen things which are radio loud, things which are radio quiet, things which show both broad and narrow emission lines, other AGN which show only narrow emission lines, and so on. So are they manifestations of the same thing, or are they completely independent kind of objects? So now meaning over the last 20-25 years or so, a consensus view has emerged that what we are looking at is essentially manifestations of the same internal phenomenon. The internal phenomenon has some variations. Okay, there are variations in the accretion rate, which decides the luminosity of the AGN. There are strong variations in the spin of the black hole and the surrounding material in the accretion disk. Higher the spin of the accretion disk, higher is the probability of forming radio jets. So we see all kinds of phenomena with radio jets, many AGN with no radio jets at all, but some others which have spectacularly powerful radio jets. And then the third area of variation, of course, is with regard to the geometry. And this is what is the focus of this figure, is that something which looks, the same object will look like some other object depending on your viewing angle. So let us try to understand on this side. So there are two kinds. So just because we want only one figure, what they've shown on this side, what a radio loud AGN will look like. And on this side, they've shown what radio quiet AGN will look like. The essential difference between the two is that in one case, there is a radio jet, and in the other there isn't. Of course, this can't be the same object, because if there is a radio jet, there'll be a radio jet, symmetric radio jet on the other side, right? But let us look at this side of the figure. So here you have the accretion disk, you have the dusty torus that surrounds it, and you have the black hole at the center. And if there is a jet that emanates out, and if you are looking straight down the axis of the jet, you will see that object as a blazar. Okay, it may be a BL-lac. Okay, it may be an optically violent variable to blazar. Now, if you're not looking straight down the barrel, but you're looking at a relatively small angle away from the jet, you will see a radio loud QSO, right? And this jet, which is moving towards you, will be relativistically boosted. So you will see it quite clearly. If it goes out and forms a lobe or something, you'll see that as well. But the counter lobe, counter jet, which is going in this direction, you will not see very brightly at all. Very likely you will not see it at all, right? So that's your radio loud QSO. Now let us understand what are the kind of clouds that that can form. Okay, so very close to the nucleus, where the temperatures are very high, the clouds that form or that exist or are falling in or going out or whatever, or in orbit, these clouds will have a high velocity dispersion because they will have a higher temperature in general. And because of the higher temperature, the range of velocities that the gas will have within that gas cloud will be quite large. And because of that, the emission line that is coming from that broad line cloud or broad line region will be Doppler broadened into a broad emission line. So if an emission line is emitted by this cloud, then you will see it as a broad emission line. As you go further out, further and further out, what happens is the temperature goes down. And as the temperature goes down, the velocity dispersion of the gas cloud goes down. And therefore, the gas cloud begins to emit not broad lines, but narrow lines. Correct? So you will see narrow line emission from clouds over here. You will see broad line emission from the clouds which are close to the radio galaxy. If you look from this region where you can see the broad line clouds quite clearly, this will appear to you as a broad line radio galaxy, which means that you'll see the radio lobes, jets, etc. If you go and get an optical spectrum of the galaxy, you will see broad lines. Will you see narrow lines also? Yes, you'll see broad lines as well as narrow lines. Now, if you look at it down this direction, are you able to see my cursor or not?
No, sir.
Okay. Let me, I think there is a way of starting the cursor. Yes, spotlight. Are you able to see it now?
Yes, sir.
Okay. So suppose you are staring down this direction. Now the torus has begun to block your view. And what does it block? It blocks your view of the AGN itself, right? But it also blocks your view of the broad line emission clouds, correct? But what will you still see? You will still see emission from the narrow line clouds. There is no problem. And will you see it as a radio galaxy? Yes, absolutely. You will see it as a radio galaxy, and you will see it as a narrow line radio galaxy. This optical spectrum will have only narrow lines, and it will be a radio galaxy. Now let us, so this radio loud side we have explained. Let us come to the radio quiet side of the diagram. Here you will see this object as possibly a Seyfert-1 if you're not staring down it directly. If you're looking this way or this way, actually, you might see it as a radio quiet QSO. Now, what is the difference between a radio quiet QSO and Seyfert-1s? We saw the difference is primarily not in the spectrum, but the difference is primarily in the luminosity. The Seyfert-1s or radio quiet QSOs have very similar spectra but different luminosities, and the Seyferts have much lower luminosities than the radio quiet QSOs. Correct? So both of these will see both broad lines and narrow lines, right? And since there is no radio emission coming, they will see no jets and no lobes and so on. Now, the situation with Seyfert-2s is very similar to the situation with narrow line radio galaxies, wherein you will see narrow lines, but you won't see the broad lines, because the line of sight to the broad lines will be blocked by the dusty torus. Now, remember, this transition from Seyfert-1 to Seyfert-2 is not black and white. And you see this similar transition in the spectrum. Okay, it doesn't go that either you'll have no broad lines, or either you'll have broad lines or you'll have no broad lines. There are some where Seyfert-2s where you do see broad lines, but they are weaker than the broad lines that you see in Seyfert-1s. So it's not a black and white kind of change. So there are, in the Seyfert category, you will see, if you look at catalogs of Seyferts, or you look at individual Seyfert galaxies, there are some Seyfert galaxies which are called Seyfert 1.5 galaxies, which means they are sort of intermediate between Seyfert-1s and Seyfert-2s, which means part of the view is blocked by the AGN, okay, or it's partly blocked, not part of the view. Because remember, this torus, etc., so you may be seeing part of the emission, but not the entire emission, or you will be seeing, as we shall see, more likely reflected emission, right? So this is now a broad picture which has been verified in various ways, and in the remaining 3 or 4 lectures we will come across many examples where the AGN unification model is supported with observational data. Okay, so now there is a problem with detecting these type 2 AGN, right? What are the type 2 AGN? Seyfert-2s or their high luminosity equivalents, which are type 2 quasars, type 2 QSOs. They may or may not have radio emission. So how do we find observational evidence for the existence of type 2 AGN? Any thoughts? We'll go back to this picture. You want to detect emission from this. How will you detect it? Because you're not seeing the central engine directly. What emission will you see definitely from the dusty torus?
Infrared emission.
Correct, right? And it's at different temperatures, so there'll be lots and lots of infrared emission from the dust. So if you do an infrared survey and maybe cross-correlate it with a radio galaxy survey, right? The radio galaxy tells you this object is an AGN. Then you find the optical counterpart, and then you obtain infrared observations of this. What will you see? You will see. So that is one way of detecting the type 2 AGN, right? You can also see that which we saw already, is that the broadband colors of AGN are different for star forming galaxies and AGN in the mid-infrared bands. So if you have access to a telescope like WISE, you will use that to use WISE colors to determine the likely AGN candidates. So that is another way. Any other way? What about X-ray emission? See, remember, we think of this as a hard solid, I mean, almost like a hard solid object. It's not, right? It is optically thick to optical radiation. So very little of the optical light comes through. But if you have X-rays, which have wavelengths which are much, much shorter than the typical diameter of these objects. So we are talking of micron sized or submicron, of the order of micron sized dust particles, right? If the X-rays have much shorter wavelengths, then it's not going to interact much with the dusty particles, and it's going to go through. So X-ray emission will also be seen, right? So if you see, if you cross match, let's say radio emission with X-ray emission, that invariably is a AGN. So you if you don't see it in the optical at all, or if you take an optical spectrum and you can't tell whether it's an AGN or not, then it very likely is a type 2 AGN. Okay, so one interesting idea which has been used to test the AGN unification hypothesis is through polarization. Observations of the spectrum of Seyfert galaxies in polarized light. So now let us look at this example. Those of you who are photographers will recognize this. So there is a lake here, and somebody has put a polarizing filter. And what does the polarizing filter do? It can, the light that is reflected off of the surface of the lake is polarized. So if you align your polarizer axis to the angle of polarization of the polarized reflected light, you will see a very clear reflection. You can, of course, turn the polarizer through 90 degrees and then you won't see any reflection. Over here, what's happening is we are seeing with our eyes, we are seeing both the polarized light in the reflection, right? But we're also seeing the unpolarized light that is coming from outside, okay? And therefore, the polarized light is not dominating, because here we are cutting out a lot of the unpolarized light, right? So the contrast is improved. We are able to see the reflection clearly. So it's clear that light which gets reflected from a liquid surface or even any other surface, reflected of dust, reflected of a gas, right, will be polarized. Right? So we see this kind of emission in the form of reflection nebulae in our galaxy. So this is the Pleiades star cluster M44 Kritika Nakshatra. And here what you see are these bright stars, bright young stars in the open cluster, but you also see diffuse emission coming from here. Now people went and studied this emission and they said this is a reflection nebula, right? If this is a reflection nebula and not an emission nebula, what would you expect to see if you took a spectrum of this? And contrast it with the spectrum of an emission nebula.
in emission nebula, there will be unpolarized light, and in
Yes.
reflection nebula, there will be a polarized light for
Correct.
the Brewster effect.
Correct. Correct. What else will the spectral lines be different between the two? What will the spectrum of a reflection nebula be like? Okay, come on.
Like a diffraction pattern.
Sorry? No, first tell me what the spectrum of a emission nebula, sorry, a reflection nebula will be like. If I take sunlight and I reflect it with a mirror and then pass it through a spectrograph, what spectrum will I get? Spectrum of the sun, right?
Yes.
It's just sunlight. So therefore, in this reflection nebula, what spectrum will you get? Spectrum of the star that is emitting, right? So there will be very few emission lines. Stars don't have, I mean, these are very bright stars. They may have a few weak emission lines, but let us say very few emission lines, right? So you will see lots of absorption lines. You'll see a few emission lines because these are early type stars, and that's it. Whereas if this were an emission nebula, what will you see? Which will be the most prominent line if this were an emission nebula?
H alpha.
H alpha, that's correct. So you will see the H alpha line, Lyman alpha line, H beta line, all those lines will be there in your spectrum, correct? So this is the difference. So now reflection doesn't change the spectrum of the object that you're looking at, right? But it does change the polarization, right? This will be polarized, like you correctly pointed out. The reflection nebula light will be polarized, unlike an emission nebula light. Okay. So, Seifert 1 and Seifert 2 unification. Question is, why do we still see the continuum in Seifert 2 galaxies? Right? We are not able to see the accretion disk. We are not able to see the black hole. Why are we still seeing fairly strong UV continuum? Not as strong as Seifert 1's, but still relatively strong. Right? The answer to this question is as follows. This is what is happening. So there are gas clouds in the outer regions. They act as reflectors of the light that is coming from the central engine, and it gets reflected and it reaches us. So although we can't see the engine itself, we are able to see some of the light reflected of the gas clouds that are in the surrounding region. So suppose you want to do an experiment to verify this. Suppose I give you a spectrum of a Seifert 2 galaxy. Okay, how will you verify that this is correct?
Sir, if there is reflection, then the light coming from the scattered continuum should be polarized.
Correct. That's absolutely right. And if you look at the spectrum, what is the difference between the spectrum that's coming from here and spectrum that's coming from here?
The spectrum that is coming from the reflection will be much of like emission spectrum.
Yes.
And the spectrum that is passing through the clouds will be absorption.
No, these are things are very hot. Okay, so the reflection,
yeah.
Everything is emitting actually, right? and they are not, their covering factor is not 100%. So nothing blocks the light completely. These are small clouds. So you can see emission from the clouds. You can also see the central engine directly, of course, if your viewing angle is correct, right? But what you're on the right track. What you see is as follows. So this is a technique known as spectropolarimetry. So which means you take a spectrum, you make a measurement, but you take spectrum of unpolarized light as well as polarized light. So this is on the top panel here is a Cepheid-2 galaxy called Markarian 348. In AGN, these things will occur quite commonly, right? 3C refers to the third Cambridge catalog. Markarian 348 is a catalog produced by Markarian and number 348 galaxy in that. Now, if you take an Markarian 348 unpolarized spectrum, right, full power spectrum, what do you see? You see predominantly narrow lines. You see a few broad lines, okay? This is, what line do you think this is? The wavelength scale is given here.
H alpha.
H alpha, correct, right? 6563 angstroms. But the moment you take a spectrum of this galaxy now in polarized light, which is shown in this lower panel, immediately, what do you see? What has happened? These lines are more or less the same, the narrow lines. What has happened to the H alpha line?
Amplitude of flux got increased and noise also comes.
Yeah, so the H alpha line, if you notice, has become much stronger than what it was here, right? I think this may be the N2 doublet that surrounds it, but may not be. Just focus on this line, which is the H alpha line, and usually it's a broad line, right? In any AGN spectrum. This broad line has become much stronger than what it was over here. So what are we seeing? We are seeing reflected lines from the broad line, reflected light from the broad line region. So there is light which is emitted here. It is producing broad emission lines. It goes there, and some of it gets reflected into our direction. So not, of course, everything gets reflected. It's not just the lines get reflected. So the continuum also gets reflected. So although in Cepheid-2s, we cannot see the inner part of the accretion disk directly, through this kind of reflective phenomena, we are able to see emission from the regions which are not directly accessible. Okay. Another thing that you expect to see is that if you go and image a galaxy in the narrow line, right? What do you expect? See, suppose you have this kind of structure, the torus is there. So as you go, so you should see an emission cone on both sides, right? This is your cone. So if you are looking at a galaxy, let us say the black hole is here at the center. If you look at it in narrow lines allow you to follow the structure to larger distances than the broad lines. Here it's a Cepheid-2, so broad lines are not even visible. This is another Markarian object, Markarian 78. And in the top line panel, it's imaged with the Hubble Space Telescope in the narrow line O3, which is a forbidden line. Here you see this kind of cone structure is visible on both sides. And if you go and observe it in the radio, this particular object is also emitting in the radio, and this is a 3.6 centimeter fairly high frequency observation with the VLA. And there you see some radio emission from the center corresponding to somewhere here where the black hole and the AGN are hidden, and jets emanating. So we also expect, if there is a jet from this kind of structure, that the axis of the jet and the axis of the cone must be the same. right, or well aligned. And we see strong evidence that this is more or less horizontal, and this too is more or less horizontal, the radio axis of the jets. So we are seeing a situation here where you're seeing narrow line emission from the narrow line clouds, and we are seeing the emission from the radio. Getting the resolution that you need to actually directly map the narrow line clouds is possible with telescopes like the Hubble Space Telescope. So with this has been done for other galaxies as well, and can be done, has been done quite extensively for the nearest and one of the brightest Seyfert-2 galaxies, this is prototype of the Seyfert-2, NGC 1068 M77. This has been observed for many decades. So it's one of the most well-studied Seyfert-2 galaxies. In this case, so you have an optical image and you measure the nuclear regions. You see some emission. Part of it will be from the narrow line clouds, right? Then you go and take only this central region and you image it with in the radio, and you see the radio jet on arc-second scales. So the radio jet is sort of in this direction. Then you go and say that, okay, maybe the AGN is right there. Okay, I'll go and image it now with VLBI, which is again in the radio, but now with VLBI techniques. The scale here has changed from 1 arc-second to 0.01 arc-second. And when you do that, you begin to see emission from the central engine, or perhaps some of it reflected or off the from the obscuring torus. So this is the sort of signature of the torus. And the important thing to notice here is that the axis of the jet and the direction of the torus are perpendicular to each other. As now this one can be very likely this is not the emission from the torus, because you shouldn't see any emission from dust in the radio, right? What this is very likely showing you is the part of the unobscured part of the central engine. It is not necessary that the torus is one solid object without any gaps. It is possible that there could be gaps in the torus. So some of the light from the central engine could leak through. And very likely that is what is happening over here. So people went and studied this galaxy now with optical and mid-infrared interferometer, which is called the VLT interferometer. VLT is a large, is a set of 4 optical telescopes operated by ESO. And they have a mode in which you can do optical interferometry, just like radio interferometry. And therefore, you can improve the resolution to the separation between the two of the telescopes. So this was done about in 2003, and they were able to obtain fringes from this interferometer. It's very hard. There isn't enough UV coverage to actually image it properly. But from the information that they gathered, they were able to prepare this artist impression of what is happening in NGC 1068. So there seems to be a central engine. There seems to be radio jets going off in both directions, and surrounding the accretion disk of, so accretion disk probably is this part. Surrounding the accretion disk are large clouds of dust and gas, which are emitting. The dust is emitting quite strongly in the infrared, in the mid-infrared bands, which can be studied with this VLT interferometer. Okay. Now let us shift gears a little bit to the X-rays and see how the X-rays provide evidence for the existence of type 2 AGN or obscured active galaxies. So this is an image of the moon taken with the Rosat space telescope, Roentgen satellite. This is a proportional counter which was there on this particular telescope. PSPC it's called. PC stands for proportional counter. And it went and took a image of the moon, right? Now, what they noticed several things. First thing, they saw the moon. This was a sort of crescent moon. They also saw some emission from the dark side of the moon. We will not go into that more. You can read up if you like. Now, first of all, what is this X-ray emission from the moon itself? From the bright side of the moon?
It's from the reflections from the sun.
Yeah, it's just reflected sunlight. Remember, the sun emits quite strongly in the X-ray. Where does the X-ray emission from the sun come from? Where is it coming? Is it coming from the inner part of the sun?
From corona.
Correct, corona, right? Remember, if it's X-rays are produced in large numbers in the inner part of the sun, but because it's optically thick, to X-rays they cannot escape, right? So they get absorbed, scattered, and so on. What we see as X-ray emission from the sun is coming from the hot corona which surrounds the sun. That is optically thin, and any X-rays that get generated in the corona can travel through space and reach us. So this is just reflected coronal light. But the third thing which was very interesting is that all around the moon there seemed to be emission in the X-rays. Now, why do we see X-rays, all of these emission, why is it seen as individual dots? Do you know how X-ray observations are made? Yeah? In X-ray,
Yes.
Yeah, go ahead.
Yes, sir. There are, I think, some mirror configuration, like Volter one mirror configuration.
Yes, there's a mirror and all that. But what do you tag? What do you count in X-rays?
Events of individual photons.
Correct. That's absolutely right. What you count in the X-rays are individual photons. We call them events, and you can tag. So whenever a photon comes in, you tag it with the time it came in and the energy that it had, right? So unlike optical telescopes where you don't count individual photons because there are many millions, billions, whatever it is coming in at the same time. With X-rays, one photon may appear and then 2 seconds later another photon will come in, like that. So you can count individual photons falling into different pixels of the detector. And clearly there seems to be a lot of emission, X-ray emission, which is coming from outside, far beyond the moon, right? You can actually estimate how much of it is coming from within the moon or at distances less than the moon. Okay. So if you subtract this sort of local background, even then there is significant X-ray emission from the outer parts, from the far away. Now, people tried to investigate whether it is coming from the disk of the galaxy, and it didn't seem to be restricted to the disk of the galaxy. It was isotropic. The moment it's completely isotropic, you begin to suspect extragalactic origin, right? It must be extragalactic. And now we know that this is what is called as the X-ray background. This X-ray background, or the diffuse extragalactic X-ray background is probably a better name for it, has a few % of the energy density of optical IR backgrounds. So X-ray background is 10 raised to minus 17 Hertz per centimeter square. Optical background is about 100 times more, and the CMB is about 100 times stronger than that, right? In the current universe. Now meaning after this was discovered in 1962 with the first X-ray observations. These were mostly balloon based at the time, or rocket based, not balloon based. Sorry, they were rocket based experiments carried out by Riccardo Giacconi and collaborators. And that won Riccardo Giacconi the Nobel Prize in Physics in 2002. Just the early experiments with X-ray instrumentation and the discovery of the X-ray background. Now we are able to have much better X-ray telescopes, and we are able to study the X-ray background and conclude that it must be generated almost entirely through AGN, many of whom are obscured by dust. And even if it is obscured by dust, the harder part of the X-ray spectrum goes through. And how do you know this X-ray background corresponds to AGN? You know it by resolved deep X-ray observations. So we have now telescopes like XMM and Chandra, which have far better resolution than the earliest X-ray telescopes, and therefore we can study what the X-ray background is due to. When you study the X-ray background, you have to explain both the energy spectrum, I mean how much of X-ray background there is, and the shape of the spectrum at the same time. And this has been done now, and it is done by modeling the X-ray background as being caused by a substantial population of type 2 AGN. So the type 2 AGN, which we said are hard to detect in the optical because you don't see the central engine, very hard to identify. We said we can identify them via radio galaxies. We said we can identify them with mid-infrared emission, but now we can also identify them via their X-ray emission. And the number counts are consistent with what one would expect given the sort of opening angles or the size of the torus. This also allows you, the relative fractions allows you to estimate how many, what is the opening angle of the torus. So if you take Seifert 1s and Seifert 2s, right? And let us say that the Seifert 1s are, let us say, half the population. Then that will allow you to constrain the opening angle of through which you can see the AGN directly. It allows you to constrain the thickness and the size of the torus. The inner edge of the torus, remember, is constrained by the sublimation radius, because anything closer, the dust will get destroyed, right? So we know what the inner radius of the torus is, but we don't know how thick the torus is. And that can be estimated or constrained by looking at relative counts of Seifert 1s and Seifert 2s. Right. The cosmic gamma ray background has also been studied, and towards the end of this course, we look at the gamma ray background also. And that is mainly due to AGN, but not type 2 AGN, but the exact opposite, the most type 1 AGN you can have, which is beamed AGN. Although some more exotic components are still possible. So the X-ray background has been fully explained, but the the gamma ray background still has some room for other more exotic phenomena. By exotic phenomena, one means basically when you see gamma rays, are they produced by mergers of protons and antiprotons, or electrons and anti-electrons, particle-antiparticle annihilation. So there is some scope for that, but very small. Okay. the optical counterparts of X-ray sources are mainly quasars, but also a few regular galaxies, as you can see in the lower panel. Right? These are optically very faint. So the torus is blocking most of the light. So these objects would not get selected as quasars in any optical survey. It's only by observing them through the X-rays are we able to say that, okay, this object could be a quasar, very heavily obscured, very faint in the optical. But if we can go and get a spectrum for it, it turns out that it's a quasar. Right. So these are all AGN. These are probably weaker AGN, maybe Seyfert galaxy counterparts, and the rest are counterparts. So by just counting the X-ray background and accounting for what you see as resolved objects, you find that you are able to find all of them or account for the X-ray background in a total way. So I think we'll stop here. Let me see what this last slide. No, we'll cover that next time. Any questions on today's class? Okay, if not, we'll stop. But before we stop, I just wanted to remind you that over the weekend, I will add the list of seminar papers. Just a small indication, you are advised to choose one from the list. Okay, but if you find some other very interesting paper that you want to describe, then please write to me, and if I think it's an appropriate paper, that's fine too. But I'll put up at least 30 papers or so. So there is a reasonable choice for you to go through. If you're selecting your own paper, remember that you only have 15 to 20 minutes to present it. So I'm going to choose for you papers that are of reasonable length. I'm not going to give you review papers which are 60 pages long. Similarly, if you choose a paper on your own, please choose a paper which is about, say, 5 to 10 pages so that you can cover it in appropriate level of detail in 15-20 minutes. Don't choose a 50-page paper. Okay.
Sir?
Yeah.
Sir, I had emailed you the list of emails. So did you get it?
Yes. I got that one in. Thanks. Yeah. So I will send out an email once these papers are on the web page. I will send an email to all of you. So Swarnim, you're confident this is the complete list from your side, right?
Yes, sir. Of those who are attending, taking the course.
No, because there's some confusion in the initial list that I got. I think I got more people on the list, particularly from the universities. And I think some of them have dropped out because we never saw them. I mean, the numbers that I have from the first lecture, when I asked you for introductions, we had about 14 people in that lecture. So those are the numbers I'm seeing every day.
Yes, there were a few university students who are not taking the course. So they told me that they're not doing it this term. So
no problem. So, so you have excluded their emails.
Yes.
Okay, great. Sounds good. Okay, so we will meet. There are only 3 lectures left. I will give all of them next week. So by the end of next week, the coursework, I mean, the teaching will be over. And then we'll be left with the assignments and the seminar. Okay, thank you.